My name is Abbie Martinez. This is my Lab 1 Constant Velocity Lab Report introduction. So the purpose of this lab was to use Newton's second law, the momentum principle, to create both a computational and a measured model of the ball's predicted motion and later analyze the principle's accuracy using those models. So Newton's first law is that an object in motion will remain in motion unless acted upon by a net force. Our system is a ball, and the surrounding is the gravitational force, or possibly friction, as the ball moves across the floor. Newton's second law are these formulas seen to the right, which is the green is the update velocity formula and the purple is the update position. Both of these are used in our code later on. Importantly, F net equals 0. Because both mass and delta t are positive values, F net must equal 0 for the change in velocity to be constant, to be 0. These are both models indicating what that would look like given constant velocity. So our main results of this experiment is that in order to accurately predict the future velocities in motion, the change in time must be small. As the distance increased, the models became further apart and were more distinct in their slopes. The net force did not equal 0 since we saw these differences in our model, meaning more interactions are happening with our system models. Our initial values are listed to the right, and I used a typical coordinate system to predict or to track my motion. So since my ball was moving from the right to the left, it was moving in the negative x direction. Observed model. This is my ball that I rolled across the floor. I used a ruler as my calibration stick, and I collected the data, giving us the graph on the left. This is our observed model experiment. So generally, we recorded a video and we uploaded it to Tracker. You can see the purple where I selected my origin and the ball is moving from the right to the left. The delta x over t was generally the same, as you can see in the middle graph. And then on the top, it varied more in the up and down direction with the y-axis, since my ball did not roll in a straight direction. We gathered the initial velocity from the first point and the second point, as indicated here. This math is the math I did to gather that initial velocity that we later use in our computational model code. Our values are here. The formulas from previously discussed are both directly in this code in line 59 and 61. F net is equal to 0 as previously discussed, and a while loop allows us to calculate that for every delta t discussion. So as we can see, at the beginning, they were very, very close together before 0.5 seconds. And then after that, they began to diverge more. And you could tell the distinction, meaning that the blue, which is what they're supposed to be, or the predicted, is very different from the experimental, and red, which is becoming more flat, if that makes sense. So that means that there are other forces interacting with our system. Both of them are linear, but they diverge, meaning there's a difference. F net does not equal 0. So we can also see this first law that should say flatter, since red is experiment model. So one possible explanation for this difference could be friction, since friction is not accounted for in the model position, since generally friction would not interfere with that, but it does in the real world. So that's why there's a difference. Possible sources are that we had to pick the points by mass very distinctly, and this is difficult to do when the ball is kind of blurred, as you can see on the left, and it didn't quite. It was kind of difficult to find the exact center of the ball, which may cause differences in both the delta x and the delta t and y, so it did not move in a straight line. Also, I pushed the ball in a way that it did not move in a straight line, causing these differences as seen on the bottom graph. Conclusions. And that can also slow down the ball. So what if the ball pointed instead, or if the ball instead continued to move in the left direction, but that was the positive? Essentially, the slopes would stay the same, but would change sign. So they would flip. And we can see this on the left versus the right. The delta T would still be the same, but that difference would account for that. What does it mean? Resistant forces like friction or air cause the net force to not equal zero. So there are infinite amounts of pushes and pulls that can be summed together to equal a zero net force.